Hello, my name is Aiden Stark. In this video, I'll discuss my experience in ENPM 701 Autonomous Robotics, along with my implementation for tackling the class's final project, the Grand Challenge. To introduce the course, ENPM 701 is a hands-on robotics course where students, such as I, got to build and program our own robots. Through a series of smaller projects, the class progressively builds the skill sets needed to tackle the Grand Challenge of the course. Some of the class projects I did during the course were the following: tracking objects via color thresholding, calibrating and tracking distance with ultrasonic sensors, tracking objects with color and shape detection, calibrating and controlling a servo gripper with PWM signals, and using accelerometer in conjunction with motor encoders to localize a robot. In the top video, you can see the projects where I performed object detection on a green arrow, and by detecting the arrow's vertices was able to determine its orientation. In the bottom video, you can see a robot's view perspective of its own gripper and with the duty cycle display in the top corner. This is where I calibrated the gripper. These projects built up to the Grand Challenge. In the Grand Challenge, students have 10 minutes for the robot to autonomously navigate a 10-foot by 10-foot field to retrieve 9 colored blocks and transfer them to the goal area. There are 3 red blocks, 3 green blocks, and 3 blue blocks, which are located within the cluttered environment. Blocks must be returned to the goal zone in order of red, green, blue, red, green, blue, red, green, blue. The robot will start within the landing zone. Students are free to mechanically modify and program the robot however they choose, but the robots may never touch the perimeter walls or receive outside assistance. Throughout the course, I built the robot shown. The robot used 4 motors attached to wheels to drive through the field, along with a servo-powered gripper to acquire blocks. To aid in sensing its environment, the robot has an ultrasonic distance sensor to detect objects in front of it, an accelerometer used to detect its heading and orientation, rotary optical encoders to keep track of the distance the robot drives, and a camera to see and identify colored blocks. To operate these sensors and actuators, the robot has an H-bridge motor driver that powers and controls the motors, and an Arduino Nano tasked with getting data from the accelerometer, and a Raspberry Pi which serves as the main processor of the robot. For programming, I use the Raspberry Pi operating system, Python, and OpenCV for all my computer vision applications. I'll now discuss my main strategy for tackling the Grand Challenge. From the starting zone, the robot will face a cluttered environment and slowly sweep counterclockwise, scanning for blocks with its camera. It will first scan the environment for a red block. Once it finds a red block, it will execute a sub-process I call get block, detailed on the next slide. When get block is executed, the robot will have acquired the red block in its gripper and know its global location in the field from its rotary encoders and accelerometer. Using this data, it will turn to face the center of the goal zone using the accelerometer, then drive the appropriate distance using the rotary encoders to position itself in the center of the goal zone. Once there, it will release the block. Using the accelerometer, which keeps track of the robot's orientation, the robot will realign itself to face the cluttered environment. It will sweep in a clockwise turning motion to find the next colored block, in this case green, until it finds it within the camera. Once found, it will execute the get block method again. With a green block acquired, the robot is instructed to drive back to its previous position. Only for the first block does the robot use global positioning to drive to the goal zone. For every other block, the robot drives back to its previous position, which should approximately be in the goal zone, after executing the get block method. Once back in the goal zone, the robot will sweep counterclockwise to scan for the color of the previous block, in this case red. It will then drop off the current block at the location of the previous block. This process allows the robot to pseudo-relocalize itself after dropping off every block. In the process of dropping off a block, the robot always corrects its position by using the previous block as a beacon. Now that I've covered the general process for how the robot tackles the Grand Challenge, I'll discuss the get block method. Once a block of the desired color has been detected by the robot, it will observe the block's position within the camera view. It will look if the block is left or right of the center line. It will then execute a series of small pulse turns. Small pulses of power are given to the motors to turn the robot in incremental amounts. After each pulse turn, the camera frame is re-examined to determine if the block is centered. Once a block is centered, the robot will calculate the distance to the block from how large the block is within the camera frame. The robot's perception of the block becomes more reliable as the robot gets closer to it, so the robot drives forward towards the block in steps. After each step towards a block, it will re-examine if the block is centered and how far away the block is. If the block is not centered, it will center the block before driving straight again. Once the block is within 15 inches, it will open its gripper, drive forward, and then grab the block. During each execution of a turn or straightforward motion, the function will summate every change in the x and y coordinates of the robot. Once the function ends, it will return the relative change in the robot's position from where it was. That is the general procedure for how I get a block. Now I'll discuss how I detect a block. To detect a block, I first pre-process the image by converting it from BGR to HSV color space. I then apply color thresholding to mask out the desired color within the image. With the desired color masked out, I find all the contours within the image. Sometimes due to noise, there are either small portions of the block missing or small pixels that are positive. This can lead to contours inside of the block, making the robot think it sees small blocks within the actual block. To correct this, I filter out any contours that have a small area or are fully encapsulated by another contour. Lastly, I apply CV2.moments and CV2.bounding rectangle to identify the center of area and the bounds encapsulating the block. To get the distance to a block from the camera, I experimentally determine two equations, one that gets the block distance from its perceived height and one from the block's perceived width. The height and width of the block is acquired from the dimensions of the enclosing bounding box previously discussed. By taking a tape measure and recording a block's distance, height, and width, I created the two graphs shown and fit an equation to each. This equation was then used to acquire the block's distance. Something important to note, though, is that the equation is more reliable the closer the block is to the camera. Looking at the far left side of the graph, we can see the block's height and width change minimally past 40 inches. Above 40 inches, the line starts to become vertical. In other words, the equation gains accuracy as the block gets closer. This is part of what inspired the Get Blocks method incremental step approach when going towards the block. As the robot gets closer, its understanding of the block's true distance improves. To grab the blocks, I used the gripper mechanism shown. During initial testing, a challenge I encountered was that blocks could tip over when they collide with the gripper. To correct this, I designed and 3D printed my own jaws for the gripper. The jaws shown extend downward towards the floor. This ensures that the gripper collides into a block and makes contact at the base of the block, not the top, preventing the block from tipping. This design allows the robot to safely run to blocks that impede its pass to the desired block, pushing them out of the way without tipping them over while the gripper is closed. I'm now going to discuss some of the challenges I encountered when working on this project. One of the biggest challenges was floor reflection. Both in the lab environment and at home, the shiny reflection of the floor made so the robot could see the reflection of the block in the floor. Since my robot determines block distance from width and height, this threw off my distance detection. To correct for this, I had my program check the aspect ratio of detected blocks. If the aspect ratio indicated much taller height than normal, the program could identify that I was seeing a reflection. To compensate, it would only use a width calculation when determining block distance, since it knows perceived height is incorrect. Another major challenge I encountered was wheel slippage and accelerometer drift. Since the robot's wheels are incapable of pivoting, every turn it performs intrinsically requires wheel slip to be executed. Additionally, due to uneven floor surfaces, the pivot center of the robot was inconsistent. It would sometimes pivot at the center, at the front wheels, or at the back wheels. Combining this with the slow drift of the accelerometer, the robot very rapidly accumulated error in its understanding of its global position. This made localization difficult, is what necessitated my approach of using the blocks themselves within the goal region to relocalize the robot after every drop-off. I'm now going to discuss some of the previous strategies I considered implementing, but decided against. First was using the ultrasonic sensor to relocalize the robot. The idea was to use the robot orientation along with perceived distance to the wall it is facing to relocalize itself along one axis. Turn to face the other axis and do the same. However, the walls of the Grand Challenge Arena were made of cloth, which poorly reflect sound waves. This made the ultrasonic sensor effectively unusable for relocalization. I'd also considered using A-Star to perform path planning and determine the most efficient path for grabbing blocks whilst avoiding other blocks. However, as previously discussed, the robot can only reliably determine where blocks are relative to it within 40 inches. This would necessitate moving closer to blocks to determine their locations accurately. However, since the robot's localization accumulates error quickly, the global position of the block will still be poorly understood as the robot moves closer because the robot is quickly losing track of where it is. Lastly, I originally intended for the robot to turn and face the blocks in one swift motion as in the video shown. I originally did this by having the robot detect the exact location of the block relative to the robot. Then having the robot perform all the trigonometry necessary to determine the angle the robot would have to turn to face the block. While this worked for the project I initially designed this algorithm for, when I went to apply it to the Grand Challenge, it did not work. This was again a limitation of the robot not well understanding block distances past 40 inches. Now that I've fully discussed my strategy and challenges in tackling the Grand Challenge, I'll show you my best run and discuss what it is doing as it is doing it. First, you can see that the robot has just done a pivot turn to align itself with the red block. You can see that it's stopping and going each time it is iteratively correcting and centering the red block within its field of view. Now that it has gotten the red block, it has used its global understanding of where it went to get to the red block to position itself within the goal, and now sweeps to find a green block. You can see it's currently doing several pulse turns to center the green block within view. It is now using its local position to where it just was before it grabbed the green block to return to the goal. It is now doing a sweeping motion to try and find the red block. It hones in on the red block's location and drops off the green block at the red block's location, thus relocalizing the robot's position within the field. That has been my Grand Challenge presentation. Thank you.